Hi students, now we are going to derive the relation between torque acting on a body and its angular acceleration. So for that, let us consider this rigid body represented by the red outline. That's the rigid body, and it is assumed to be made up of so many point masses, elementary masses. One such point mass of m, its mass is m, I have represented. So when the entire body is going to rotate about a fixed axis or point, so this is the fixed axis or the fixed point about which the particle is going to rotate is O. So when the entire body is turning, each and every particle present in the body will make circular motion. Understand that? So the particle of mass m, after some time it takes a position here and then here, like that everywhere it changes the position, so that the trajectory or the locus of all its positions, if you join, means you will get a circle, and r will be the radius of the circle. Now r vector is called as what? Position vector of this particle or the point mass m. Okay. Now what will happen if a force F acts on this particle, which is making an angle 90 degree with respect to the direction of the position vector. So what is the angle between the position vector and the force vector is 90 degree. So that now the particle as well as the rigid body is going to experience the maximum torque. Understand? So first I will start with the expression, that is torque tau. So torque tau is equal to r vector cross product f vector. Okay, so this is equal to r into f into sine 90 into unit vector. So the magnitude of this torque is given by tau is equal to r into f into sine 90 is 1. So this is r into f. So this is the required equation number 1. Okay, students. So what is the torque experienced by only one point particle, one point mass, that is given by what? The tau equal to r into f. So now we have already studied that in circular motion, every particle of the body possesses two velocities and two accelerations. So one is linear acceleration A and the other one is angular acceleration alpha. Is it not? Okay. Also, the linear acceleration of this particle is equal to what? F by m, or what is the force acting on the particle, that is equal to m into A as per Newton's second law. So here F is equal to mass of the point particle into its linear acceleration. If I substitute F is equal to ma in this equation, so tau is now equal to r into m into A. So this is step number 2. Okay, I said there are two accelerations for the particle in circular motion. Okay, body is in rotational motion, but the path of every particle is circular inside. So they will possess two accelerations, namely linear acceleration A and angular acceleration alpha. Okay, so the linear acceleration A is equal to radius times the angular acceleration. So that I am going to substitute. Okay, step number 3 is the relationship between linear acceleration and angular acceleration. Alpha is the angular acceleration. So for A equal to r alpha, if I substitute, therefore what will be the magnitude of the torque? Tau is now equal to r into m into r alpha. Is it not? So r into m into r alpha. So tau is now equal to m. R into r is r square. So this separately I will keep it in a bracket. And the last term is alpha. So this is step number 4. So what terms I have written inside the bracket? It is the product of mass of the particle and the square of its distance. The square of its distance from the axis. So for the particle which we have considered, only one particle I have considered, and what is its mass is m, and its distance from the axis is only r. Similarly, some particles may be closer to the axis with a short distance, some end particles may be at a large distance, each particle is not at the same distance. So now if I will consider all the particles and find the product of their masses and the squares of their distances from the axis and add, okay, so what is going to happen, I am going to explain to you. So before that, this quantity m into r square, what role it is going to play in this expression? The product of mass of the point particle and the square of its distance from the axis is going to resist the rotational motion of the rigid body. So it is going to, this term is going to offer some opposition to the rotational effect of the body, and this quantity m into r square is called by the name moment of inertia. Moment of inertia of the point mass, about the fixed point O, or about the fixed axis passing through O. So m into r square is only the moment of inertia of a single particle. Suppose if I will add like this moment of inertia of the second particle, third particle up to the nth particle, if I add all their moments of inertia, then that will be called as the net opposition to the rotational effect of the rigid body by all the particles. Understand? So now this is the moment of inertia of the point mass. Okay. Therefore, now the torque. Okay. Therefore, for the entire rigid body, I can write torque tau is equal to sigma mr square. So mi or I square also I can represent. So this bracketed quantity mi or I square with the sigma, this is a summing up of n number of terms starting from I equal to 1 to nth particle. Understand? I am adding the moment of inertia or the opposition offered by each and every particles present in the rigid body. So into this alpha, okay, into alpha, and this is now equal to I into alpha, where, okay, this sigma mi ri square starting from I equal to 1 to the nth particle is called the moment of inertia of the rigid body. So without sigma mr square alone is called the moment of inertia or the opposition offered by only one particle. So this is the net opposition. Sigma mr square means what? The net opposition, total effective opposition to the rotational motion of the rigid body by all the particles present inside the body. Understand that? So that only is called as a moment of inertia of the rigid body about a fixed axis. Okay. So tau is equal to I into alpha. So what is the topic of discussion is torque, relation between torque and angular acceleration. So left side is the torque and the right side is the angular acceleration. So this is in scalar form I have written, only the magnitudes I have written. Understand? And in vector form, tau is a vector, moment of inertia is a scalar quantity, it is a constant, and alpha is a vector quantity. So in this picture, suppose if this is the direction of rotation, then the tau vector will be upward. Understand? And alpha, angular acceleration vector also will be upward. That is why tau vector and alpha vector, no, they are directly proportional to each other. Both are in the same direction. Okay. So if this tau and alpha are in the same direction means body will accelerate. Suppose tau is upward and alpha is downward means the body will retard. So you can take while switching on the fan, initial rotation is very slow. Next continuous rotations will be of higher angular speed, and finally it takes up the maximum rotational speed, and in this case alpha and tau are in the same direction. When you switch off, what happens? The acceleration is now in the opposite direction to that of the torque. So the fan slows down and finally stops because these two vectors are in the opposite directions. So this is the vector form of the relationship between the torque and angular acceleration. Now if you compare this equation, you see here tau is equal to I into alpha can be compared in linear motion. A similar equation we have studied in linear motion, translatory motion, we have studied F is equal to m into A. Is it not? Here itself we have used the same equation already. So this particle possesses two accelerations, one in linear motion, that is translatory. It may not be straight line, it may be curvilinear also. Understand, this equation is common for what? Rectilinear along a straight line or curvilinear along a circle. So force is equal to mass into acceleration. Is it not? Like that, tau is equal to moment of inertia into angular acceleration. The first equation is in a translatory motion. The second equation is in rotational motion. So if you compare, the torque is playing the same role that is played by force in translatory motion. The role played by torque in rotational motion is equivalent to the role played by force in which motion? Translatory motion. Similarly, the opposition to the linear motion of a body is its mass. In the same way, the opposition to the rotational motion of a rigid body is its moment of inertia. So, A is a linear acceleration and alpha is angular acceleration. So, I can say that torque is a term which is analogous to force. Understand? And the moment of inertia is a term which is analogous to the mass of a body in linear motion. Like that, alpha, the angular acceleration, is analogous to the term linear acceleration in the translatory motion. So, my dear students, tau is equal to I into alpha. This is the relationship between the torque and the angular acceleration. I hope you must have understood well. Fine.